Welcome listeners to another lecture on the subject fundamentals of geology. So, the next topic, that is plate tectonics, is obviously an extension or a continuation of the earlier lecture on continental drift. So, as the topic suggests, plate tectonics, it is actually the dynamics of the plate that we can observe across the globe from the present, as well as we can interpret the dynamics of the plates from the past as well. But again, how this concept of plate tectonics came into its existence. So, as we have seen earlier in the last lecture, the theory or the hypothesis of continental drift, that Alfred Wegener presented the hypothesis of continental drift, and also later on other geologists like Hess and Sir Arthur Holmes, they also pioneered the concept of the plate tectonics, which obviously is an modern version, or you can say a more scientific way of explaining things under the broad hypothesis of continental drift. So, talking about again continental drift, what Alfred Wegener couldn't explain, that what is the mechanism, that how the continents are moving. Later on, Hess and Arthur Holmes, they explained that how the movement of the plate can be explained by the different processes that are operating within the earth. And to start with, again we will look at the cross section of the earth, starting from the center of the earth, that is the solid inner core surrounded by the liquid core. So, this liquid core, which is obviously ferromagnesium and nickel in content, mainly iron and nickel are present in liquid state. So, this is having a density of around 17, then followed by your periodic mantle, or the main constituent of the mantle is peridotite, which is also dominantly iron rich, but obviously not as dense at the as that of the core, and it is having a density of around 6 to 7, and followed by the top part that represents the crust is having also a relatively less density, that is for the oceanic crust. It actually has two components, the oceanic crust and the continental crust. So, the density of the continental crust varies between 2.7 to 2.9, and for the oceanic crust is varies between 3.1 to 3.3. And as we can see, as the lighter or less denser material floats over the high density material, so that also suffices or explains the stratification of the earth from the core, mantle, and finally to the crust. So, looking at the upper crustal level, or at the continental crust and the upper part of the mantle that also defines the lithosphere, it beneath it you have a plastic material, or the nature of the rock here is plastic in nature. It is not similar that we can relate it like a polythene or a plastic bag, but the rocks here, they tries to flow under the influence of high temperature and pressure, because it behaves in a plastic manner due to the presence of 1% water in the asthenosphere, which is obviously behaves in a plastic manner. Whereas the lithosphere, that is the combination of your crust and the upper part of the upper mantle that make up the lithosphere, it behaves in a more rigid and brittle manner in comparison to the asthenosphere, which tries to flow in a plastic manner, or which behaves in a plastic manner. So, again talking back about the idea, or the initial idea, that the continental crust, which are mainly granitic in nature, they are surrounded by your basaltic oceanic crust that are surrounding these continental regions, or the granitic crust. But strictly speaking, granitic crust does not mean only granite in composition, it also means a group of rocks that are also referred as granodiorite. So, it is a combination of granite and granodiorite, and they look extremely similar. So, broadly we are speaking or we are using a collective term, that is granitic for the continental crust material and basaltic for the oceanic crust material. So, now if I simply compare this mechanism with one of our common household phenomenon, that is, if you are boiling some water just over an oven, then you can see that as the boiling starts, the cold water that is going into boiling, it loses its density and it becomes light, and finally it upwells in uh, a symmetric manner like this, and as the hot water comes up, your subsequently your cold water tries to go down in this kind of a container. Now, if I simply increase the size of the container, like a fish poacher, it is not a common thing that we means use generally, but in this kind of container you can actually poach the whole fish. So, it is a long elongated container, and generally to run a fish poacher we need two ovens simultaneously. So, if I simply compare this idea that you have two heat source like this, and continuously your water is boiling within this large container or an elongate container like this. So, in that case what you can see that there are sites where your boiling water is or your hot water is coming up, and there are also sites here in between the sides of the hot water, there are also zones where your cold water are going down. So, this is a continuous process. When you are boiling some water in a container, it is a continuous process. So, your hot water will try to move up, as well as your cold water will try to subsequently it will try to go down towards the center of the container. And you can see there are these zones. If I now compare, then there are at least two zones just above the main heat source where your boiling water or the hot water is rising up, as well as there are zones here. In this case there are three zones where your cold water is going down within the container. So, now if I place this and I compare this with the scenario of the earth, then I can simply take a wooden block which is obviously having around a density of 0.5 and water as it is having a density of 1. So, the wooden plank will definitely float on the top of the water, and if I put three heat sources now beneath the container, then what will happen that there will be these zones, these multiple zones of hot water that will try to upwell within the container, as well as there are zones where your cold water is going down towards the bottom of the container. And in doing so, what is happening that on the bottom of the wooden plank, which is an analog of your lithosphere, again lithosphere is the rigid part that comprises of the crust as well as the upper part of the upper mantle. So, that makes up your lithosphere. So, at the bottom of the lithosphere, what is happening that you are getting zones of this compressional and tensional forces that are acting just below the bottom of the wooden plank. So, here if I start with this first zone, here your hot water is coming up or upwelling inside the container, and it is again getting disseminated across or just below the wooden plank. So, in a symmetrical way. So, you have a pull kind of a mechanism that is going on beneath the wooden plank at this region. So, you have a tensional force here. Similarly, the other sides of upwelling hot water will also pose some tensional forces here as well as here, where it is marked as T. That means, it is giving you a scenario of tensional regimes. Similarly, when your cold water is going down away from the zones of the hot water, here there are two scenarios, one here, another one is here. So, in these two cases again what is happening that the water is flowing towards itself, because the cold water will try to descend down the container. So, it is generating a situation where you can say that compressional or compressive forces are being acted at the bottom of the plank again. So, here are again two zones, this one and this one, which two are marked as C. So, they will have a compressional effect beneath the wooden plank. So, now if I see this together, then you can also identify that there are zones where your tensional forces will be dominant, as well as there are zones where your compressional forces will be dominant. So, here what will refer to this mechanism as the presence of convection cells within the asthenosphere, where in analog scenario your boiling water is continuously ascending and descending in a symmetrical manner, as well as your analog of lithosphere, that is a wooden plank which is exerting, or on the bottom of the wooden plank you can have both tensional and compressional forces that will act at the bottom of the wooden plank. So, obviously you can see that if we have this kind of convection cells of your symmetric convection cells of compressional regimes and tensional regimes, then they will also affect, or they will try to move the wooden plank along with it at the zones of tension as well as in the zones of compression. So, in the zones of compression, the lithosphere will try to move towards itself, and at the zones of tension the lithosphere will try to break apart. So, the hypothesis of presence of convection cells within the asthenosphere is, you can see, is the main reason or the energy source that is driving the movement of the plates. Here from now on, like I mentioned in my last lecture, that from now on we will be referring to plate, we will be not referring to continents as an individual entity. Continents are a component within the large plates. So, now your plates will have these two scenarios at certain zones. There will be zones of tension within the plate, also there will be zones of compression within the plate. Now, so if you have a zone of tension in the continental lithospheric part, obviously like I again mentioned, your lithosphere is also can be divided into continental lithosphere as well as oceanic lithosphere. So, if you have a tensional zone within the continental lithosphere, then what is happening, that it is due to the presence of this convection cells just beneath the lithosphere that is operating within the asthenosphere, they will exert a tensional force just beneath the lithosphere, leading to the upwelling of the basaltic magma. We can also think of the analog, that was hot water in the experimental stage, that the hot water is upwelling, and also if I compare this with the real scenario, then that hot water is getting replaced here by the basaltic magma, which is upwelling through the lithosphere and are generating zones of rifting or large scale zones of fracture systems, through which your basaltic magma will finally upwell onto the surface of the earth. So, there are zones of continental rift systems. For example, if I look at the first case study, then I look at the Rio Grande rift zone, which is situated in the North American plate. So, you can see that the North American plate, which is again mostly dominated by the continental lithosphere, some parts of it are obviously oceanic lithosphere, but which is mostly dominated by your continental lithosphere, you have a rift system or a rift zone sitting at the center of the continental lithosphere within the North American plate. Again, to mention, the North American continental lithosphere is a large component within the North American plate. So, here the idea is that the Rio Grande River, when it actually, it is a very fantastic example of a hot water river that evolved within the North American continental lithosphere, and but now it is no longer giving you hot water, because somehow the supply of this basaltic magma that was happening due to the rifting or the formation of rift system within the continental lithosphere has now, due to some reason, has ceased. So, this river that is present in the New Mexican region or the New Mexican state of the North American part, is this river is no longer means getting broadened. Earlier there was a channel, that channel supplied hot water under the action of the basaltic magma because of the heat of the basaltic magma that was coming just beneath the continental lithosphere. But now the broadening of this river has now ceased. So, we can say that it is a kind of a failed rift. There is no more activity along the rift zone. But again, to refer to the idea of the convection cell, here we can say, so in this Rio Grande river there was a scenario like this where your hot basaltic magma was rising beneath the lithosphere under the action of the convection cells, and likewise this basaltic magma tries to flow symmetrically beneath the lithosphere, leading to the formation of the fracture system within the relatively rigid lithospheric material or the continental lithosphere of your North American plate. So, after this, again if I look for an answer, that is North America breaking up, obviously if this process would have continued for long a period of time, this has now ceased. So, the answer to this question is obviously no, that no, North America is not breaking up. But if it would have continued, this rift system would have continued to grow in size as well as in width, means length as well as in width, then it would have been possible that the North America might also break up into two halves, like we get to see the spreading of the mid-Atlantic ridge, where they were together during the Gondwana land or during the time of Pangea, when your South America and Africa, they were together. Rift system got developed within the margin of your South America and Africa, and then that rift evolved finally into a mid-oceanic ridge, separating the two halves of the Gondwana into, on the west side it is the South America, on the east it is the Africa. So, it is, you can say, the initiation of the formation of the continental breakup, but somehow luckily or fortunately this process has now ceased. So, presently your North America is not breaking up, but it initiated as a rift system. The Rio Grande River initiated under a rift zone. Now, if I also compare this with again a simple example, if I take a piece of cake, a large birthday cake, and if I try to simply remove the base of the cake without interrupting or without directly touching the top of the cake, then also if I remove or try to remove the base of the cake, then automatically by moving the base of the cake you can also generate certain fractures, or you can also generate some divide within the, you can say, relatively softer part of that particular cake. And if it continues, then it grows larger and larger without any break in the asthenospheric material, because it is molten in nature and it can flow. So, your convection cells that are moving beneath the lithosphere will not give you any breakage, because it is already plastic in nature. So, the material will try to flow, but the lithospheric part, which is rigid in nature and behaves in a brittle manner, then that lithospheric part will try to break up into subparts, and they might also give you the generation of a rift valley. And if this process continues for long and long, then finally these two part of the continental lithosphere, if I am referring to continental lithosphere, they will finally get separated from its origin. Now, if I look at a different case study of the Great African Rift, then you can see parallelly a few scenarios. The first one is the opening of the Red Sea. Red Sea, you can say, is a linear ocean, like we can also will come back to this. So, Red Sea, you can see it is obviously a sea that is connected to the Indian Ocean, but it is more or less linear in pattern, as well as there is Gulf of Aden, which has already which is no longer only linear, it is more of like a triangular rift system which has evolved into a mid-oceanic ridge. So, you can see the formation of a mid-oceanic ridge, but the Red Sea is not a completion of the process of the rift system. So, there is also still there is some rifting going on along simply across the Red Sea. So, your mid-oceanic development of mid-oceanic ridge is not yet complete, and if I can compare it with the first case study of the Rio Grande River in North America, I can say that this is actually the initiation of the first rift within the Africa. It is can be compared with a different scenario as well, like that of the separation of Madagascar. It is believed that Madagascar separated from the rest of the African and continental lithosphere by the process of a rifting, which is now complete. That is why the continental lithosphere of the Madagascar island is now completely detached from that of your African continental lithosphere. So, your great African rift, we can also see nowadays, means in recent years there have been reports of channeling of seawater through the great African rifts in different parts, specifically in the means eastern part of Africa, where your seawater is continuously coming in inside the land. So, this marks the great African rift, actually marks the first initiation of a rift system. You can say the second stage is the formation of linear ocean that we get to see in the Red Sea region, where your rifting is still under process, and also the Gulf of Aden, which is now you can say the rifting is complete and the development of a mid-oceanic rift system is now under process. So, this this eastern part of Africa gives you natural examples or natural laboratories to study both the initiation of a rift system, also the intermediate stage of a rift system, also your completion of a rift system and transformation into a mid-oceanic ridge, that you can see the development of a mid-oceanic ridge is taking place here. So, this part of Africa can give you the natural examples of three stages of rifting, starting from the initial rift that we have also seen in context to the North American plate, as well as the formation of the Gulf of Aden, which is now being transformed into a mid-oceanic ridge. So, like rifting, also parallelly what is happening, like the presence of rift system, and obviously that is getting transformed at some point of time, will be transformed into a mid-oceanic ridge system. What is happening is that you are creating new oceanic floor with the help of new basaltic magma that is coming onto the surface of the earth. Similarly, whatever volume of basaltic magma is getting created, you have to also destroy that amount of basaltic magma somewhere in the earth, otherwise the volume of the earth or the surface area of the earth will definitely increase with time. So, you can't ruin that balance. So, this balance can be only achieved by the consumption of basaltic material or the ocean floor basalt, older ocean floor basaltic material along the subduction zones across the earth. So, why the subduction is going on? There is a very common question, that is it always it is true that the ocean floor is getting subducted beneath the continental lithosphere. Is it possible to have a scenario that is other way around? That means the continental lithosphere is going down between oceanic lithosphere? No. The answer is obviously no, because like again the factor of density, that the ocean basalt or the oceanic crust is having, or the oceanic lithosphere is having a density of around 3.1 to 3.3 maximum, and your continental lithosphere is having a density of 2.7 to 2.9 in value of your density. So, obviously the higher density material will always subduct or bow down between the less density material. So likewise, any subduction that we get to see on Earth, the first probability is the formation of continental arc system, where your ocean floor basalt is getting destroyed or getting subducted beneath the continental lithosphere. The other scenario is that the oceanic lithosphere is also getting subducted between another beneath the another ocean lithosphere. So here again, one question that comes to my mind is that if in the second scenario your oceanic lithosphere is getting subducted between another oceanic lithosphere, then there you are not having a density difference like we get to say in the first case, where your oceanic lithosphere, which is having a higher density relative to that of the continental lithosphere, is simply bowing down between the continental lithosphere. But in case when your oceanic lithosphere is getting subducted beneath another oceanic lithosphere, in that case what is happening, that it is nothing but a factor of age, that older the oceanic lithosphere, means relatively the older oceanic lithosphere will bow down or subduct beneath the younger oceanic lithosphere. Again, that is also a play of density, because older the oceanic lithosphere, the density will be higher in that case. So likewise, again, if I compare this to the global scenario now, that your new oceanic lithosphere is getting created at the mid oceanic ridges and your older oceanic lithosphere is getting destroyed at the continental arc, or be it another island arc system, where your oceanic lithosphere is bowing down beneath the continental lithosphere, then you can see there is a age difference between this, because as we move away from the mid oceanic ridge system, where your new oceanic floor is getting created, as we move away from that towards the continent, there will be always your older oceanic lithosphere that are present at the edge of the continent. So as the oceanic lithosphere grows old, it finally gains the density, it gets more and more denser in comparison to the continental lithosphere, or be it some other oceanic lithosphere. Finally it starts to bow down, or it gets subducted beneath your continental or some other younger oceanic lithosphere. Finally, so you can see this cycle of generation of new ocean and floor basalt, which is the new oceanic material you are adding, or new oceanic lithosphere you are adding at the mid oceanic ridges, as well as you are destroying the older uh, oceanic lithosphere material at the subduction zone. So it's a very cyclic process that we can see, and this cyclic process, the main phenomena that is driving this cyclic process is nothing but the presence of convection cells within the asthenosphere that are driving. So again, if I relate it with the convection cells and the experiment of the boiling water, then I can see that at the site of the mid oceanic ridges, where your new oceanic lithosphere is being created, these are the sites of your tensional zones, where your convection cell will pose some tensional forces beneath the lithosphere, as well as when we are referring to the subduction zone, in that case your convection cells are giving you a compressional scenario. So there is a balance between this tensional scenario and the compressional scenario. One is resulting into the eruption of the basaltic magma on the ocean floor, another is a result of the consumption or the destruction of basaltic magma at the edge of the subduction zone. Then again, if I look at natural examples, then you can see along the western coast of South America there is huge this large Andes mountain belt, which is nothing but a continental arc system, where your Nazca plate, which is associated with the Pacific plate, we will talk about that later on. So your Nazca plate here is actually getting subducted or is bowing down beneath the South American continental lithosphere. So your oceanic lithosphere that belongs to the Nazca plate is getting subducted beneath the South American continental lithosphere, resulting into the formation of this continental arc, as well as obviously they always result into the formation of mountains when you are referring to a continental arc system. So there are obviously continental arc volcanoes that are present all along the margin of the South American coast, the west coast of South America. For example, there is a small country that is Guatemala. There you can see 17 volcanoes all along that are present along the Andes mountain belt. There is another example here which refers to your island arc system. These are island arc volcanism that are present all along the Aleutian Trench, where this is the part of Alaska, this is your part of Russia. There you have this continental lithosphere. Here also you have continental lithosphere, but in the Bering Sea, here you have the oceanic lithosphere, where your Pacific plate is again getting subducted beneath this island arc system, generating this Aleutian island arc system, which is an island arc system again. And to remember that your oceanic lithosphere can get consumed or can get subducted beneath a continental lithosphere, which is an example of this Andes mountain belt, where you have this continental lithosphere and your oceanic lithosphere is getting subducted beneath this continental lithosphere. Again, if I talk about the Aleutian Trench, your Pacific plate, which is obviously oceanic, is getting again subducted across this Aleutian Trench, where both are oceanic lithosphere. Obviously, the Pacific lithospheric part is older, and that is why it is also denser than that of its other half of the Aleutian Trench. Now, if I look at the Pacific Ocean, if I look at the bathymetric map, that means it is actually map of the ocean floor. If I simply take out the water from the Pacific Ocean, the ocean floor will look like something like this. So, these are your zones of subduction like this. This is Japan, then you have this Philippine Islands. All along this you have the subduction zones, you have this Aleutian Trench. Again, here you have the San Andreas Fault, there is also subduction going on. Here again, in this part, again the other half of the East Pacific rise. So, your East Pacific rise that you can see here is nothing but the mid-oceanic ridge, which is giving material both to the Pacific plate as well as giving material to the Nazca plate. As this a plate, and from the definition of the plate we have seen that a plate is invariably bound on one side by a mid-oceanic ridge and on the other side by a subduction zone. So, if I am referring to this as the Nazca plate, then on one side you can see the presence of the East Pacific rise, which is obviously a mid-oceanic ridge, and on the other side you have this Andes mountain belt, which is also a subduction. So, this part within the subduction zone on the right and a mid-oceanic ridge on the left, this part is your Nazca plate here, as well as here you can see the larger Pacific plate, where on three sides the Pacific plate is getting consumed along the Japan Trench or the Aleutian Islands, or be it the San Andreas Fault. In all these regions the Pacific plate is getting consumed or destroyed, but remember that the East Pacific rise is also active. So, it is continuously adding to the oceanic lithosphere, new material, new basaltic magma are being added on the Pacific plate from the East Pacific rise. So, here again I would like to simply ask one question that should obviously means important, that whether the Pacific plate as it is being consumed on three sides, whether it will retain its surface area or it will be consumed completely, and due to the consumption or the destruction of the complete Pacific plate, finally Japan may collide with the North America. So, it depends, it is nothing but it depends on the rate of how fast new ocean and floor basalt is getting created at the East Pacific rise, as well as the balance between this new ocean floor being created at the East Pacific rise and the consumption or the destruction of the Pacific oceanic lithosphere along these three trenches that are present on three sides of the Pacific plate. So, on one side you are generating new material or adding new material to the Pacific plate, on the rest of the three sides you are destructing the oceanic lithosphere that is already present on the Pacific plate. So, it is again a balance, whether that balance will be maintained or not throughout the Earth's future, that depends on several other things. So, just to remind of this, that always there is a balance, or there is a relative balance across the globe. It is not restricted, the balance is not always restricted to a single plate. The balance is achieved due to the rate of destruction and rate of construction, or the rate of newly evolving basaltic magma on the ocean floor, as well as the rate of destruction of the older ocean floor basalt. So, there has to be a balance between this. Okay, so like I was discussing about this bathymetric map. So, we will first end our discussion here on the bathymetric map, that how your subduction zones and mid-oceanic ridges are associated with a plate, and next we will go to the different examples of subduction zones and mid-oceanic ridges, and we will be looking into some animation, so that we can understand that how mid-oceanic ridges and subduction zones work. Thank you.